All right, so I am going to prove proof 2.4, which basically is the proof that if you have a closed subset of a Hilbert space, a convex closed subset of a Hilbert space, I should say, that the closest point to that subset to any point x in the subspace must satisfy this property, which is that, so if k naught is the closest space in our k subset, x minus k naught, the inner product of that with any other point k in big K must be less than or equal to 0. So how are we going to prove this? First, what we do is we say let delta be the infimum of this. So the little k's element of big K are convex subset, closed convex subset. We're going to say that this is how close we can get in this infinite sequence. Now we want to show that there's actually a k naught that minimizes that we don't just have a infinite sequence and we never actually minimize it. We always just get closer and closer to some delta. So what we do first is we construct a sequence k sub I such that this norm converges to our delta. Now we want to show that our x sub I, and actually this should be k sub I, my apologies, is Cauchy. And so how we do this is we take advantage of the fact that we are in a Hilbert space and that we can then use the parallelogram inequality, parallelogram law, I should say. So here on the left-hand side, I have the fact that the outside edges of a parallelogram, 2 times the square of their length, must be equal to the squared length of the two diagonals on the inside of the parallelogram. And now I know that because I've constructed these sequences such that they converge to the infimum, I can choose some n that's large enough such that for all I greater than n and for all j greater than n, I have this. So it's going to be greater than the square of delta plus epsilon squared over 2 for both of these terms. And if I add those up, I get epsilon squared. On the right-hand side, I have this, which is like the Cauchy sequence term I care about. And then I also have this piece here, which basically just says that this is the other diagonal. So this is the squared length of the diagonal. And here I'm multiplying it by 4 because this is like the half length of that diagonal. So if I need to get the full length of the diagonal, I multiply that by 2. And if I square it, I get 4 times that half length squared. And I know that because I have a convex set k, k sub I plus k sub j divided by 2, that's a convex combination of the k's that are in my set. So I know that that's also in my set. And because I know that's in my set, it must be greater than or equal to delta by the fact that I have this here, that I've said that the smallest possible value is delta. So on the left-hand side, what I end up with is that on this side, I have this number here plus 4 times delta squared. So if I subtract 4 times delta squared on both sides, I'm just left with epsilon squared must be greater than or equal to k sub I minus k sub j squared. And so this is basically Cauchy then, because I can get rid of these squares and I just have epsilon is greater than the distance between k sub I and k sub j. And because I have this sequence that's Cauchy, and because this sequence is actually located in a Hilbert space, I know it must be convergent. So I'm going to say that it converges to some k sub naught, which is an element of my Hilbert space. And actually it also converges not only to my Hilbert space, but it actually converges to a point in my convex set k, because I specified at the very start that that convex set k is closed. Now that I've shown that this k sub naught exists, now I'm going to show that it must satisfy the property that its inner product, x minus k sub naught, and then k minus k sub naught must be less than or equal to 0. So what I do is that I define this interpolation between some k sub 1 that I pick, that can be anywhere in my convex set k, for any alpha between 0 and 1, this is how I'm going to define it. And then what I do is I look to see what is the square distance between x and this k sub alpha. And if I rewrite things and I use the inner product and I kind of FOIL things out, what I end up getting is that this is equal to a squared times the distance squared between x and k sub 1, a minus alpha squared times the distance between x minus k0, and then I have this term here, which is 2 times alpha times 1 minus alpha times the inner product of x minus k0 and x minus k sub 1. Now what I do is I take this and I take the derivative with respect to alpha, and then I evaluate that derivative when alpha is equal to 1. And so when I do that, I get this term here. And now I'm able to say that this is always greater than or equal to 0, that this norm is always going to be increasing in alpha because of the fact that I've already said that k sub 0 is the, or k sub naught is the closest point to x. And if this is my k1, as I increase alpha, I'm just moving away towards k1 away from k0. So it must be the case that I'm actually increasing the distance between x and whatever point I'm creating, interpolating. So that's why I'm able to make the argument and be able to say that this has to be greater than or equal to 0. And then it's just a matter of doing some algebra here, and I end up, after I go through this, showing that I have the desired inequality here. And that is proof 2.4.